Okay, so I will continue about the spin orbiters and I will talk about the theory side. So I think I don't have to talk much about antiferromagnets in general, and why we are interested in antiferromagnets, because we already heard many thoughts on this topic. So one thing I will say is that the big problem with antiferromagnets is that the magnetic order in antiferromagnets is quite difficult to manipulate. And this was the reason why we started to be interested in the spin orbitor. And so we wanted to find some method which would allow some efficient manipulation of antiferromagnetic order. And in particular, we would like an electrical method, because for microelectronic applications, this is of course the most practical way. And we know from ferromagnets that electrical switching is actually the best for memory applications. And so in ferromagnets, there are several different methods which can be used for electrical manipulation, and I will talk about this in detail in the morning, so I don't have to talk much about this, but I just want to summarize. So we have the spin transfer current, which relies on existence of transmission of spin polarized current from one ferromagnetic layer to another. And then we have the spin orbiter, and again, as we heard in the morning, there are actually two different mechanisms which are called spin orbiter, or they are somehow also called differently. So we have a mechanism where we have electrical current flowing in this direction, and then because of the spin Hall effect in this non-magnetic material, we have a spin current flowing in this ferromagnet, and this is sometimes called a spin Hall torque or spin Hall effect, spin orbit torque. But we have also another torque which occurs in bulk, and this is due to the inverse spin galvanic effect. And this one also contributes in this case, because this one requires a broken inversion symmetry, and this interface breaks the inversion symmetry. But in this bulk case, we have no contribution from the spin Hall effect. And I will talk only about this bulk spin orbiter, which is one we started to focus on, which is in part because it is maybe easiest to describe theoretically and also experimentally, maybe because this kind of torque will require very thin layers, which is very hard to make, especially with antiferromagnets. And it's also true for this kind of torque, but for this torque it occurs to the bulk, so we don't need such a torque. Right. So, as I said, the origin of the spin orbiter, this bulk spin orbiter, is the inverse spin galvanic, or so-called Edelstein effect, which means in a material with broken inversion symmetry, electrical field creates some non-equilibrium spin polarization. And this effect has been demonstrated, but in a non-magnetic material it's not so interesting because the spin polarization is small. But if we have a material which is magnetic, and the spin polarization interacts with the magnetic order, it can even switch it. And so then this is more interesting. And so in antiferromagnets now, what we realized is that the spin polarization which is generated by the current doesn't have to be uniform throughout the unit cell. And here is an illustration of how we would like it to look. That when we have the opposite magnetic moments, we will have opposite spin polarizations, and as I will show in some materials with some symmetry, this can indeed be achieved. And then because the exchange interaction is short range, we expect that this spin polarization will interact only with the magnetic moment on this and lattice, and we will have a torque acting on this, which are maybe different. And so before I will talk more about the spin orbiter and about the theory of the spin orbiter, I want to say a bit more about what kind of fields, what kind of effective magnetic fields we need to switch antiferromagnets. And we already know on this, we also heard many times from Helen and other people, that uniform magnetic fields are not very efficient at manipulating antiferromagnetic order. And so the lowest field which can reorient an antiferromagnet is the spin flow field, which is proportional to the square root of the anisotropy in the exchange field. And because the exchange field is quite large, this is typically large field, around 10 Tesla. What we need instead is a field which is staggered in a collinear antiferromagnet, so which has the same order as the magnetic order, which for non-collinear antiferromagnet mean some kind of non-collinear magnetic field. And this is something we haven't studied much in detail, it's mostly in the collinear case. And I just want to show here as an illustration why this field is so efficient for antiferromagnets. These are equations for the dynamics. They are derived under very simple case where we assume for the antiferromagnet we only have the staggered field, no uniform field or no damping. And then if you compare with the equation for ferromagnet, you see that, this is equation for a ferromagnet and a uniform magnetic field. You see that the staggered field enters the equation in the same form as the uniform field in ferromagnet, directly competes with an isotropic field. This already tells us that the critical value of the staggered field for switching will be the anisotropic field, just like in the ferromagnets. But you already see also from this equation that the nature of the dynamics in the antiferromagnets is quite different. You see there is this J, which is the exchange constant, which is not present here in the ferromagnetic equation, which means the dynamic will be much faster in the antiferromagnet. We also see that the equation is second order, so there will be inertia. And also the form of the dynamics is quite different. So in a ferromagnet, the magnetic moment will recess around the equilibrium direction, will move on a cone. While in an antiferromagnet, if you write this equation in the limit of small anisotropy, you find it's actually equation of a simple pendulum. So what happens is that this narrow vector moves on a plane rather than on a cone. Right. So I said we need the effective field which is staggered, and so we of course cannot create such effective field, and we cannot create such a field externally. We need to create it somehow internally, and so I will show you how we can do it with the spin on the torque. And so we describe the torque via some effective magnetic field, and we can always do this because the torque is always perpendicular to the magnetic moment. And now I just want to show a little how I said that the spin or the torque is generated by the non-equilibrium spin polarization, so I just want to say something about how this effective field is actually related to this non-equilibrium spin polarization. And so in the simplest case which we can consider this kind of coupling of this conduction electrons, this as a spin operator of the conduction electrons, and the time is just direction of the equilibrium magnetic moment. This Hamiltonian is sometimes called as the Hamiltonian. And this is quite simple. This is the simplest case we can consider, but qualitatively we expect this always to be the case. There will be some kind of coupling between the equilibrium magnetic moments and the conduction electrons. And then we can easily find the effective field that we see in this case. It is actually proportional to this non-equilibrium spin polarization. In the marginal case, it doesn't have to be exactly proportional, but it will always be somehow, it will be similar to this relation always. Right. And then, so how we actually calculate this, we use the linear response theory, and I will not go into any details. What I just want to say is that always when we calculate any transport property, the most difficult part is how we describe this order. And we so far have been using only the constant gamma approximation, which means we essentially broaden all the bands by the same amount, which is quite a simple approximation that works quite well in many cases. But then we expect some contributions will probably be missed. For example, if we use this for the spin Hall effect, we would miss the skew scattering or the side chain contributions. So here I show some calculations, and we first did the calculation for manganese and gold. I'll just show here the copper manganese arsenide because it has actually the same symmetry, and this is the material where the experiments were done. And so when we calculate the effective field, we find that it has this Rashba-like symmetry, so it is always perpendicular to the applied electric field, and it lies in plane. And we also found, so it can be written approximately by this formula, and I will talk more about why it has precisely this formula. And we also found that the magnitude of the field is quite large actually, so it's around 3 million Tesla per 10 to the 7th per centimeter squared, which is of course still quite a small field, but this is comparable to what we have in ferromagnets, where we know that this switching can work. So I just show this as an illustration of the calculations we did. But mostly I want to focus on talking about the symmetry of the spin orbital. Because we found that to understand the spin orbital symmetry is really crucial. And so one thing we found that we have to do is, if we want to understand the symmetry of this effective field, we have to separate this field into a part which is even under time reversal and into a part which is odd under time reversal. Which seems a little strange because normally we would think that the magnetic field should be even under time reversal. Or sorry, odd under time reversal. But this is because this is some non-equilibrium process which generates the field which includes dissipation, and then this is an effective field which doesn't have a cyclic behavior in time reversal. And this is something we have to do for all the transport phenomena. And so we separate into an even part, and then we define this linear response tensors, and I will talk about the symmetry of this. And so one first question which we always want to understand is, when will the spin orbital exist? And we know in ferromagnets that we have to break the inversion symmetry, and this is very easy to understand why that is, because if you write this kind of equation for this non-equilibrium spin polarization, under inversion the spin is invariant, under inversion the electric field will change sign. Then we see that if the material has inversion symmetry, then this linear response tensor has to be 0, and there can be no current-induced spin polarization. Now we write this equation for the antiferromagnets. Now we have to calculate this non-equilibrium spin polarization on each magnetic lattice. And now we see that under inversion, this non-equilibrium spin polarization in general transforms to some non-equilibrium spin polarization on a different atom. So the inversion will in general bring one atom to another atom. And so the non-equilibrium spin polarization will be prohibited only if the inversion center is in the atom itself. And so this condition is less strict in ferromagnets. We find that we don't have to break the inversion symmetry globally, but only locally, which means there must be no inversion center in the atom inside. And we can illustrate this in the example of silicon, which has inversion symmetry, of course, but the inversion center is in between the two atoms. And so if we apply electrical field, there will be a spin polarization which is opposite now on the two silicon atoms. And then if these two atoms are different, then the inversion symmetry will be broken also globally, and then there will be some net spin polarization. And we can have antiferromagnets which have similar properties to this. So copper manganese arsenide also has inversion center in between the two magnetic atoms. But you also see that the magnetic order also breaks the inversion symmetry here, because inversion will bring this atom into this one, and they have opposite magnetic moment. This was actually the reason why we first were interested in these materials for the spin orbiter, because we thought this inversion symmetry breaking will be enough to create a torque. And it does create some kind of a torque, but there is also separate inversion breaking which is local. And it turns out that for the torque, which is actually the most relevant for the experiments, it's the local inversion symmetry breaking which is the most important. And we can also have the antiferromagnets which have globally broken inversion symmetry, and there will also be a torque, because if the inversion symmetry is broken globally, it's also of course broken locally on each lattice. And then another question which we want to answer is, when will the spin orbiter be efficient for manipulating the magnetic order? And then so we have to understand when will the effective field be staggered. And here we find in collinear antiferromagnets there are two typical cases that occur. The two magnetic sublattices can be connected either by inversion, like in this copper manganese arsenide case, or by translation, like in this copper manganese antimonide case. And we find that in the first case, it will be the even part of the field which will be staggered, and in the second case it will be the odd part. And I will talk more about how the even and odd part typically look, but you already see that this is quite different from ferromagnets, because in ferromagnets you would have both of these contributions. In antiferromagnets you also have both of these contributions, but only one of them will be efficient, the other will have almost no effect on the magnetic order. And so, the last thing we want to understand is how, turn the file. So we need to understand how will the effective field depend on the direction of magnetic moments, and this is because we are interested in some switching, and so during the switching process, of course, the direction of magnetic moments will change, and then in general the effective field will depend on this direction. And so to describe this, we expand this tensor in the powers of the direction of the Nell vector, and we study the symmetry of these terms, and we find that this is very useful because only the lowest order terms are needed. Usually, at least for qualitative description, we just really need to take the lowest order term, and we find almost everything. And then, of course, the even terms in this expansion will correspond to the even field, and the odd terms in this expansion to the odd field. And if we look at the lowest order term for the even field, this is of course independent of the L vector, and this is what we call the field-like term, and this is in many cases this is the most important term. And if we look at the first order term, this will be the lowest order for the odd field. And here, this often has this anti-damping like form, and I think people often assume that it always has this anti-damping like form, but actually the symmetry is in general much more complicated, and it always has to be linear in the L vector, but not always it's possible to write it in this form where P would be a constant vector. And the nice thing about this expansion is that the symmetry of this expansion is determined only by the local non-magnetic point group. And there are only 21 non-magnetic point groups in broken immersion symmetry, so it's not difficult to do a complete classification, and because there is not so many cases, such classification is actually quite useful, and there's not so many things to analyze. And so we can create a table like this, where this is just the field-like term for all the point groups with broken inversion symmetry, and we also can do the higher order terms. And what's especially interesting is that if we look at the field-like terms, it's because these are actually only 3 by 3 tensors, so they can only have several different forms. And we find that they can have this well-known Rashba form, which is the case in copper manganese arsenide, where the effective field is always perpendicular to the electrical current, and we can to electrical field, and we can also define this what we call a generalized Rashba, where if we rotate the electrical field, the effective field will rotate with the electrical field, but doesn't have to be perpendicular. And then there's also the Dresselhaus contribution, where if you rotate the electrical field, the effective magnetic field rotates in the opposite direction. Also, there should be again the general Dresselhaus picture, but I by mistake did the same thing. But this is the case in nickel manganese antimony, which I will talk about more later, or about in a gallium manganese arsenide, for example. And these two contributions are quite well known. There is also a third contribution, which we call WILE. Maybe I don't know if this is a good name, but this is a contribution where the effective magnetic field, or the spin polarization, is proportional to the electrical field. And so it's quite different from these two cases, because these two cases are 2D, while this one is 3-dimensional in every direction of the electrical field. And this has actually recently been calculated in some chiral materials. And so this is also quite interesting in that this can occur in special crystals. These are called chiral crystals. These are crystals in which inversion is not only broken, but it's not a symmetry even in combination with any other symmetry. And what this means is there are really two distinct crystals for the inversion partners, one left-handed and one right-handed crystal, and this kind of contribution. So I will mention a little bit about the calculations we did, mainly to show that really these symmetry arguments work, and that most of the things we can learn from the symmetry, and the calculation mostly tell us just the magnitude of the effect. And so we studied the manganese control, and also this simple 2D model where we add Rashba spin-orbit coupling. So this model simulates something like an interface. And what's interesting here is that these two models are quite different, but they have the same local symmetry, the side symmetry of the manganese atoms in these two models is the same. And because of that, when we actually calculate how the effective field in this model depends on the direction of electric field, we see in both models the dependence is very similar. And so we see that really it's the symmetry which controls primarily this dependence. And the even field here has this Rajba form, the odd field has this anti-identical form. And so we also did the calculation for the ferromagnetic nickel manganese antimonide because there have been experiments done in Cambridge by Chiara Starelli and other people. And from the symmetry point of view, this material is actually quite interesting because this material is cubic, and in its cubic form, the symmetry is very high. And this means that without any strain, when it is cubic, there will be no zeroth order term, so no field-like term is allowed by symmetry. Then when we apply some strain, then also the zeroth order term will appear, and then when the strain is uniaxial, then the Dresselhaus kind of field will appear. And in experiment, there is always some strain present because this material is grown on a substrate which doesn't have the same lattice constant. And really, in the experiment, Dresselhaus field is observed. And when we do the calculation without strain and with strain, you really see that without strain there is some strong dependence on magnetic moments. And also that the field is quite small. And when we add a strain, which in this case is I think around 1% strain, we now see an order of magnitude increase in the magnitude of the field, and we see that the field becomes almost constant because now it's the zeroth order term which dominates the field. And we can also look at the odd part of the field in this case, and this is quite interesting because this is a case where we find a field which is not an anti-damping line. So, for example, when the electric field is applied along the 1-1-0 direction, we find effective magnetic field of this form, and this cannot be written as in this form m cross p, where p would be some constant vector. And so we do not know what kind of dynamics this kind of field will induce. We have some ideas about what the dynamics of the anti-damping line would be. Probably it would be quite similar to the anti-damping line, but in general I think this is quite interesting because we can now have fields of many different types in principle. And so one last illustration of the usefulness of the symmetry arguments is this orthorhombic copper manganese arsenide, which Lieberschmickel will talk about. This material is interesting because it's predicted to be this Dirac semi-metric. And so we wanted to look at the torics in this material, and we wanted the results very quickly, so we didn't have time to do calculations, but we could just look at the symmetry and we can actually find quite a lot. So this again has this PT symmetry which connects the two, or it connects the manganese A and manganese C and manganese B and manganese D. So you see this material has 4 magnetic sublattices, which makes it more complicated. But from this symmetry we can say that if only the even part of the field can have the proper symmetry for switching efficiently this magnetic order, and then but this tells us only the relation between these two atoms and these two atoms, but it doesn't tell us anything about this relation between these two and these two. So then we can look also at other symmetry operations, and we can find general form of this lowest order terms. And we find, since the magnetic moments on A and B are the same, we also want some magnetic field which is the same in A and B. And so if we look at this tensor, we find it has some components which would be same, some components which would be opposite. So for efficient manipulation, only these components will actually matter. So in the end, we find that the efficient field will have this kind, will be described by this kind of linear response tensor, which means it will be again in plane. So it's quite similar to the tetragonal copper manganese arsenide, where the only difference is that there are these two components will have to be opposite. Right, so here I will conclude. So the main message I wanted to make is that the spin orbiter enables electrical control of antiferromagnets because it enables to create these staggered fields. And then if we really want to understand the spin orbiter, we have to understand symmetry. And then the calculations show that the spin orbiter in antiferromagnets can be as large and as efficient in antiferromagnets as in ferromagnets. Thank you for your attention.
I have one question regarding to a technological application of this current with writing antiferromagnet. So typically when you reverse the current polarity, the only thing that changes is that you come to an antiferromagnetic state which is 180 degrees different from the initial one. So is there any reason to believe that there is a mechanism that will let you come to a different state, which is maybe 90 degrees different, or maybe choose a triangular antiferromagnet to come to a state which, for example, would produce a different AMR state, so just reversing the current polarity?
Right, so in the collinear antiferromagnet, I think this is not easy. So generally it's not easy to differentiate between the state, between the 180 degree rotated state and I don't know. I mean, I think probably if you reverse the polarity of the current always, this will bring you to the opposite state, at least in the collinear. When you go into non-collinear, then things become more trivial, but we haven't studied that so much. So then you have to use this 90-degree kind of current. But in principle, you can differentiate between the 180-degree rotated states, not by linear effects in electrical field, but by higher order effects, which have been detected now. This is the spin-hole magnetoresistance. But yeah, this is I'm not sure this would be very practical because these effects are, of course, quite small. In principle, it's possible.
Yeah, combined to that, I mean, isn't it possible to, if there's a whole class of these weak ferromagnets where they are slightly canted, then you could induce a switching mechanism that can easily be better, much easier, because you also have an effective ferromagnet.
Right, you mean you detect it by this weak ferromagnetic component? Sure, we haven't really thought about that, but maybe this would also work.
And the other question I have is, you clearly indicated the symmetry arguments, but the, let's say, quantitative, how you say it's as large, but can you really calculate numbers?
Sure, yeah. So
maybe I missed that, but
we have a number here, and this I would say is about the typical value we find.
Okay.
So, I mean, we say it's large, but of course, this is a large current density. In copper manganese arsenic, it's about the limit of what you can do in microscope. You can do, I don't know, 1 or 2 orders of magnitude higher, and it's million Tesla field. But really, it's the same as the current.
You consider this symmetry always a perfect crystal, and in reality, of course, one has always not imperfection and maybe some steps and whatever. Because you consider the local field which you generated. Would you also agree that in case you would have an imperfect system with some defects, your local, your broken symmetry due to the crystal and due to the defects?
Sure.
So your effective field you would generate would actually follow the defects?
I think, yeah. So the defects for sure locally will influence the field and may change it quite a lot. But overall, we expect that the disorder, the effect of disorder will usually average out. So even in imperfect crystal, as long as it's a single crystal, the symmetry should be globally the same. But locally, yeah.
Would it average out, or would it be just make an imperfect system also switchable?
Right. So, I don't know. I think for maybe simple disorder, it probably would average. I mean, this is the same symmetry arguments like used, for example, for the conductivity tensor, where of course you also have a disorder if you measure conductivity of some material and you don't see some change. I think usually at least you don't see some change of the symmetry of the conductivity tensor because of the disorder. But in principle, I don't know, maybe there is some special kind of disorder where you would actually change the global symmetry. It is possible.
Can I add one thing? You identified that copper manganese arsenide and manganese to gold. Have you identified other practical systems where you might be able to get crucible spin-off in the antiferromagnet?
So not really, but we probably should try to look for more materials. What we can say is that the symmetry requirements are not so strict. The for many antiferromagnets, I think we should have good symmetry. So we should look at it, but so far we haven't really done anything. I think Jakub maybe calculated a little bit more antiferromagnets, but nothing which is, he's not clear, unfortunately, but I think nothing which is above room temperature. So we should probably look. Difficulty is that we need to find a material which has small anisotrope base and large torques, which is not so trivial, I think. But,
Okay, if there are no more questions, let's just thank you again.